Okay, so thank you very much. So first of all, I would like to thank the organizer for this opportunity to talk today. So I'm going to talk about heating time statistics for random dynamical system. So this has some link with the talk of Benoit Saussol yesterday. So there is two terms in this title. So there is heating time statistic and there is random dynamical system. So first of all, I will just recall what we mean by heating time statistics. So this stuff has been studied a lot in the last 20 years, and there's a lot of people in this room who know really well about this stuff. But I will just recall what we are looking at. So just take a dynamical system. That is, you have a set X and you have a map G from X into itself. Mu is a probability measure. So mu of X is 1. And it's invariant by G. That is, if you take the measure of the pre-image of a set, this is the same as the measure of this set. Okay? So if the system is ergodic, for example, it's well known by Poincaré recurrence theorem that if you take for almost every point, you will come back as close as you want from its starting point, and you will also enter any set you want with positive measures. So for example, if you take point X, you can look at its orbit under G, so this is G of X. Then you apply G again, so it will be G2 of X. And you look at the behavior of this orbit. So when you look at heating time, what you want to know if you take another point X here, that's the x0. For example, you look at a ball around this point, so for example, radius r. So you wonder what's the time you need for this orbit to enter this set. So you know that after some time, there will be an n such that Tn of x will enter this ball. So this n is called the heating time. So I will put the definition here. So I will define the heating time of x in the ball center in x0 of radius r. This is the first time. Okay, so that the orbit of x enter the ball center x0 of radius r. And what we want to know is what's the behavior of this heating time when r goes to 0. So there is a different way of studying this behavior, but when we look at heating time statistic, what we want to know if which are the points so that this is bigger than the measure of the ball. So we know that by Kak's lemma, the behavior of this return time more or less 1 over the measure of the ball. So what we want to wonder is what the measure of the point, so that this is bigger than T over the measure of the ball. And so the question is what's happened if you take r which goes to 0. So as I was telling before, this has already been studied a lot, and what you expect if your system is chaotic enough is that you will have an exponential here. But this is really well known, so in fact what I want to do is not exactly this. I want to study this stuff, but for random dynamical system. So in fact I will not have just one map. I will change a little bit, and I will take a family of map. So in fact I will have a family of map. Let's call them Chi omega, which are indexed by omega. So each map goes from X into itself. Okay, and at each step, instead of taking my map T, I will choose one of these maps. So for example, T omega 0. And then randomly, I will choose another one, T omega 1. And then maybe another one, T omega 2. And what I want to know is exactly the same thing. Okay, if I randomly choose each map at this step, when I'm going to come in this ball center in x0 and radius r. So, in fact, first I need to explain how randomly I will choose this map. So, what we do generally is we'll put a dynamic on the set omega. So, in fact, I will put some dynamics, let's call it theta, and a probability measure p, okay? And so at the first step, I will take T omega, which omega chosen according to p, and then I will apply the dynamic theta on omega. So in fact, here I will apply T of theta omega, and then T of theta 2 omega, and so on. So in fact, I will define what we call a random orbit. So it will be T n omega. So you take your point x, you apply T omega, and then you apply T of theta omega, and so on, until T of theta n minus 1 omega. Okay, so this is called the random orbit. So this will be T omega, this will be T omega 2, so on. And so here, what I want to know is when the random orbit will enter a ball center in x0 at radius r. So in fact, I'll just change my definition a little bit. So I will define the random return time. So this is the first time that heating time, the first time that the random orbit enter a ball center in x0 and radius r. And the question is, okay, I would like to look at some kind of this question, to look what are the points, what's the behavior of this heating time. So first of all, I need to put a measure here. So in fact, there is a way of studying this random dynamical system is through the skew-product. Okay, so Benoit gives a definition yesterday. So here, I take this skew-product S from omega x to omega x, and if you take a point omega x, so you apply theta on omega, and here you apply g omega on x. So if you look at this, what happened? If you apply it n times, here you will have theta and omega, and here what will appear is the random orbit. Okay, so in fact, when we say that we have an invariant measure for the random dynamical system, if we have an invariant measure for this skew-product S. So in fact, the measure I will take will be mu, which will be invariant by S. Okay. But I cannot take any invariant measure. I have some restriction because here I know that I have this measure P on omega. So in fact, I need that the marginal here on omega will be P. Okay. Okay, so what I will do is I will look at the measure here, mu, of the point. So this will be the point in omega x, such that the heating time is smaller than T over here. I need to put something, so which will be the measure of a ball. So in fact, you can see it, and Benoit told something about it yesterday, that in fact what you need to put here will be the stationary measure. So in fact, I will call it nu, the marginal of mu on x. Okay, so this is a measure that appear here for the renormalization. Okay, so this is what I want to know. So No, 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 I don't have a product measure. Okay. So there is this decomposition, if you prefer. So the measure mu, there is this decomposition on. Okay? And so nu is just the. Okay? Just another way of seeing it. Okay, so the question is, what's happened for random dynamical system? Do we still have an exponential distribution for the heating time as in the deterministic case? So what we are going to see, if you have the good assumption on your system, we will have an exponential distribution. So the assumption that you need, we already see some of it on some of the previous talk. What you hope that if you have a nice decay of correlation, you can have an exponential distribution. So in fact, I will need 3 assumptions. So the first one, which I call random aperiodicity. So I need that the measure of the point, okay, which come back exactly in the starting point is 0. So I have, okay, so the measure of the point which come back exactly at the same place, I need this to be 0, okay? Why I need this? Because imagine you have your point x, so you look at the random orbit, and you want to, so I am talking about heating time, but inside of it there is something about return time also. So if I come back exactly at the same point, there is no interest in looking at the behavior of the return time, because it will always be the same one. Okay, there is, if you take a ball around this, if you came back exactly at the same point, the behavior of it, of this return time, does not depend on the radius of the ball. So these points are of no interest, so we want to remove them. Okay. Then I will need a technical assumption that we also saw yesterday with Benoit. So for almost every point in X, so for almost every point X, okay, I need that I can find A strictly positive, B it can be 0, such that if you look at the measure of a ball around X, and you remove a smaller ball, okay, R to the minus rho, so this needs to be small if rho is small. So the radius, so this can be big, this is no problem, but I need it to be controlled by rho. Okay, so this is need to work for any r small enough and rho smaller than r. Okay, so what does this mean? If you take a ball here, you remove a smaller one. So if this is rho. If this is small, the measure of this annulus here must be small. Okay, so you have a control here with rho. Okay, and finally, what we are hoping that will appear, generally appear in this kind of problem, is an assumption on the decay of correlation. Okay, so here I will assume that for any Lipschitz function from x to r, and any bounded function from omega x to R. So I have a super polynomial decay of correlation. Okay, so what does this mean? That's the integral of phi of x times psi composed with Sn. So d mu. So this converges to the integral of phi times the integral of psi. This with, so I will call it alpha. So this will be super polynomial. I will write it after. So here there is a norm of phi and the norm of psi. Okay, so here I assume that alpha n is super polynomial. That is, alpha n times n to the p. This always goes to 0 if p is positive. Okay. So in fact, if you know a little bit of random dynamical system, maybe you are not going to like this, this assumption. So this is a little bit weaker than assuming decay for the skew. So because here I have just a Lipschitz function from x to r. But this is stronger than decay of correlation for the random dynamical system, because here what appears is a skew. So after I give the theorem, I will explain in which case we can remove S here and put some observable from X to R. So really the decay of correlation for the random dynamical system and not for the skew. Okay, so what will happen is the following. So if you have this three assumptions, so if the system is random aperiodic, so this assumption 1 is satisfied, and we have a super polynomial decay of correlation, then we prove that for every t positive and almost every x0, okay, in X, so and something here, such that the lower local dimension is strictly positive. So I will explain this after. So what will happen? We have an exponential distribution for the heating time. Okay. So the measure of the point such that the random heating time is bigger than t over the measure of the ball. Sometimes x0 for those r. This goes to an exponential when r goes to 0. Okay, so just to recall for people who don't know this, what does this mean? The local dimension of a point, so Stefano talked about it on the other day. So this is the limit of the point, of the measure of the log, of the measure of the ball over the log of the radius. Okay, so this is the limit inf here. I just need it to be positive. Okay, so I was saying before, in fact, in some case you can put something weaker here. So in fact, if you have an IID dynamical system, so I'll put this as a remark. So if the system is IID, so the random dynamical system is IID, then you can change your assumption here on the decay of correlation. So we can change this assumption by another one, which will be, so here I take the same phi, which will be Lipschitz, and I change this one by L infinity function, but now I just need from X to R. So this is really the decay of correlation for the random dynamical system. So this is the random orbit. So in fact, this kind of result, so for IID dynamical system, has already been proven for perturbation. So for random perturbation, yes. No. Here. This is a measure of omega x. Here? No, this is a measure on omega x. Yeah. Yes, it is. Okay, you can put the integral here if you prefer and put dp. Yeah, okay. And so this kind of result was already been proven by Ale Eitas, George Freitas, and Sandro Vajangi. And but it was just for perturbation. So this worked for more general system. You don't need it to be a perturbation. And also they had a stronger assumption because they assume polynomial decay, but against L1. So here I just need super-polynomial, but again L infinity. So this is much this is weaker, and this work for more general system. So in fact, this result, I'm not going to enter the detail, but this result is a really simple application of a more general result, which is for observation of dynamical systems. So what do I mean by this? So this is in fact a remark just linked with the talk about David Varandas yesterday. So at the end there was some question, and he was saying that in fact when you look at a huge dynamical system, you are not interested. It's really difficult to look at everything. So generally, what you look at some observation of the system or a projection of this system. Okay, so in fact, this is the same kind of result. In fact, when you want to study huge dynamical system, huge dimensional dynamical system, if you are just interested in some part of the system, and so you make an observation and you want to know what's happened just for this observation. For example, he was looking at the temperature. In fact, this is this center in this case, because if you look at it, and here, my dynamical system is S. So in fact, I'm not interested in all S, but just a projection of S. So in fact, what I am looking at is just the random orbit. So I'm not interested in the whole system. I'm just interested in the projection of this system in X. Okay, so just a remark. So now there is another natural question, and Benoit talked about it yesterday, is, okay, here I look at the measure of omega x. So this is a measure on the set omega x, such that the return time is bigger than t over the measure of the ball. So a natural question is say, okay, but what's happened if you fix omega? So now you fix omega and you want to look at the measure, because it's the same problem, the measure of the ball, but you fix omega. So you want to know the measure of the point x such that the return time is bigger than t over the measure of the ball. Okay, so the question is, does this have a limit? Can you prove also that there is an exponential limit in this case? So now omega is fixed. So in fact, this kind of problem is much more difficult and than looking at this problem. So until now, there is almost no work on this heating time for random dynamical systems. So there was the one I said before about ATAS, ATAS invariant. There was this one, and there was the one Benoit talked about it yesterday. So which is for the quench results. So I will recall what you talked about yesterday. So in fact, if you want to obtain a result here with omega fixed, it's much more difficult. So until now, the only results that we have are for a random subshift of finite type. So this is really a particular system that we are looking at. Okay. So now I will look at a particular family of random dynamical systems, which are random subshift of finite type. Okay. So now my set X will be n to the n. So this is the sequence. And all my maps will be the same. So G omega in fact will be sigma. So this will be the shift. I will just looking at shift. But there will still be some randomness, but the randomness is done in the measure mu. Okay? So this is the mu omega. So in fact, at each step, you randomly choose a different measure. Okay? So the map you apply is the same, but you change the measure, okay, and you can change also the transition matrix. Okay, so I will recall what Benoit told us yesterday. Okay, so in fact he explained us that if you have we needed 3 assumptions. Okay, there was 2 hypotheses of mixing and one of the technical assumption, and in this case you can obtain an exponential law. Okay, so I will recall the result. So the first assumption that we need, so here I will take A in the algebra of n cylinders and B in the algebra of m cylinders. So first we need a decay for the measure nu. Okay, so if you look at the measure nu of A intersect with n minus g b, this goes to the measure of A times measure B, and we will have alpha, so some constant here, and alpha g. So here alpha will be a polynomial. So here alpha g times g to the q goes to 0 when g goes to infinity for some q which is fixed. Okay. So this was the first assumption. So there was another one which is mixing but for the sample measure. Okay. So here if you take the measure of mu omega of the same set here minus mu omega of A, mu of theta n plus g omega B. So this some c omega times alpha g. Okay, this is for p almost every omega. Okay, so we have decay for the stationary measure, decay for the sample measure, and there was this technical assumption here that the measure, sample measure of cylinders, here, decay exponentially. Okay. No. No, this is, yeah, this is new. Yeah, it's the same assumption that he explained yesterday. So in fact, yeah, you are asking him a question. Yeah, generally this is a really difficult stuff to verify. This is quite a complicated. No, this is new. Mu is a measure, is a invariant measure by a skew, and nu is a stationary measure. This is almost. Okay, so Cn epsilon, what? This is just a cylinder. So this is a x. So just x, y. It's epsilon I. Well, I. Okay. So in fact, I will look, this time I will not look at return in ball, but return in cylinder. So I will change the notation. I will use this one, Rn. So this is the first time that point, a point, the orbit of a point, enter the cylinder. Okay. So now I will give the theorem that Benoit already gave yesterday. So this is a result with Benoit Saussol and Paulo Varandas. Okay, so if we have these three assumptions, then you have an exponential law for the sample for the heating time, but with respect to the sample measure. So for any t and almost every epsilon and p almost every omega, then it's random subshift of finite type. Yes. Yes. Yeah, I put, yeah, sure. Yeah, X is the set of all sequence. It's too simplify, but yeah, in fact, you need to check your set. No, here I just put X, I simplify, didn't want to enter in all the detail, but yes, it's a random subshift, so you can change the transition matrix. So in fact, the set you are looking at is a subset of X. So you look at when you can pass from one to another sequence. Yeah, you can, when you change your transition matrix, you will change the family of a sequence. So that's why I put X, all the sequences, but what? No. Yes. Yeah, but this the first one, no, because yeah, the state A must depend. So the cylinder that's acceptable. Yes. Yeah, but I didn't write all the detail here because I didn't. Yeah, exactly. But there is some care you need to take to do this. Yeah, I didn't want to write everything down because it will take a lot of time, and with 15 minutes, there's more thing I want to talk about. So yeah, exactly. You need to really take care when you define your random subshift because depending on the transition matrix, you change your cylinder. Okay, so this was the result that Benoit talked about yesterday. So we have an exponential distribution for the distribution of heating time. Okay. So for deterministic system, there is some result. I think it's Freitas and Todd, who say that if you have some assumption on the system, generally if you have chaotic system, for deterministic one, you have an exponential distribution of heating time. And what they prove is that if you put a stronger assumption, in fact, you have a dichotomy. So there is, you can have a result for every point, okay? And there will be the extremal index, which will appear in the law. Okay, so in fact, with Mike Todd, what we wanted to do is trying to see if it's the same thing for random dynamical systems. So if you put stronger assumption, if there will be this dichotomy. So what we prove is that it's the same for random dynamical systems, at least for random subshift of finite type. So in fact, if you put a stronger assumption here, you can prove a dichotomy. So you have a result, but for every point. Okay. So here I will change a little bit my assumption. So the first one, I will take the same one. Okay. So the second one here, it's alpha mixing. Okay. So if you want, in the deterministic case, if you want to prove a dichotomy, you need to put decay of correlation against L1. So this is kind of similar. If you put stronger decay of correlation, you will have the dichotomy. So here, the stronger one, so I will change 2 by 2b, will be psi mixing. So in fact, I will change my assumption with something stronger here. B minus mu omega A. So here, I will change my alpha mixing, okay, by psi mixing. So this means that in fact here, we have the measure of A and the measure of B, which appear. Okay. So I will change alpha mixing by psi mixing. So the third one I will change also. Here. So here I need the cylinder to decay exponentially fast. So I need them also not to decay too fast. So in fact, I will assume that they don't decay too fast. Okay. So the same for every epsilon and p almost every omega. Okay, and I will need another assumption here. So what do I need? I need that if, in fact, I know, for example, here I have A and B. I don't know anything about them, but imagine that M is greater than N, and you know that B is in A, it's a subset of A. So in this case, I need to control that I can control the measure of B by the measure of A. So I know that G decay nicely. So here I will have a function phi Okay, and what's this function? So I need that we can find a function phi, which is from 0, 1 to n, which is decreasing, and summable. Okay, so what we prove is the following. So this is a result with Mike Todd. So if now you have this assumption, so 1, it's the same one. 2, so now I have psi mixing. 3, so the decay of the cylinder, and this technical assumption 4, call it 4b, okay. Then we have a dichotomy. So that is, we have a result for every point. So the first case is if you have a periodic point. So here this is an almost a result almost everywhere. So now I can have a result for every point. So the first case is if my point is periodic. Then I have an exponential law. So the difference is that there will be an exponential. In the exponential, there will be the extremal index. So now this is e to the minus theta t when n goes to infinity. So theta here is the extremal index, and we know how to compute it. And okay, I will write it here. So here, how do we compute it? It's the limit when n goes to infinity. So we look at the ratio between the points which are in the cylinder, but does not come back after p iteration. Okay, and the measure of the cylinder. Okay, so this is a periodic case. You have the extremal index, and if the point is not periodic, you have the same results. So you have exponential law. So otherwise, for every t and almost every omega, you have an exponential law. So this fact, the extremal index is 1. Okay. So if you want an almost everywhere result, you just need alpha mixing, and if you put more assumption, psi mixing, you have a result for every point. So for periodic points, you have this extremal index, which appears the law. Otherwise, it's an exponential. Okay, so I still have 5 minutes to give an idea here of what's the difference between these two things. So yesterday, Benoit already gave the proof of our results. So just to recall what you do, how you obtain this law, you look at the difference between heating time and return time. Okay, so what the idea is that you open a gap, okay? And if you open a gap, you can apply mixing. So in fact, he proved, yes, there are 3 terms. So there was a term when you open a gap, which is you use the mixing. So this is an easy part. Then there is a probability of having a short eating time, which generally it's the easiest part. And then there is this term that you are calling GN, okay? And you wanted to prove that this goes to 0. Okay, there was this term GN, and you proved that it was going to 0. So this is the probability of having a short return time. So I'm not going to do what he already did yesterday. I just recall there was 2 important ingredients in this proof. So first, he used Ornstein-Weiss result, okay, and the other important ingredient is he used Lebesgue density point. Okay, so this was the 2 main ingredients of this proof. So when you want to have a result for every point, the proof is similar in some way. So you do the same. You open a gap, so you use a mixing. For the eating time, it's easy, and the difficult part are the short return time. So I will just give a small short ID. So the GN here, so I will call, to simplify, A will be my cylinder here. I will call A prime, so the points which are in the cylinder, but does not come back after p iteration. So I will just do the periodic part, okay? The periodic part. And there is this K, which is G over the measure of A. Okay? So this is almost the same definition as yesterday. So GN, what's GN? Is the sum of the measure of the point which have short eating time, return time. So here, in fact, I will look at the points which are in A prime. Okay, so such that the return time is smaller than G. Okay, so this is the probability of having short return time because I am in A prime, which is a subset of A. Okay, so this is a return time. And in this case, we want to prove that this goes to 0. So what you can do is some really simple approximation here. You say, okay, if I come back in G, it means that I am in the pre-image. If I come back in the cylinder, it means that I am in the pre-image of the cylinder. So in fact, I can approximate here by the measure of A prime intersect with the pre-image, yeah, the double sum. Pre-image of the cylinder. Okay, so this is a really simple approximation. And in fact, what's happened for periodic point is that, you know, if you have a periodic point, which is in this set, what does this mean? That you are in the cylinder, but does not come back after p iteration. In fact, you can prove that if you don't come back after p iteration, in fact, you will you didn't came back before the size of the cylinder. There is no way you came back before the size of the cylinder. So in fact, you can change this. You can change here and assume. So this is just, you can begin at n, okay? So there is no problem here, because if you does not come back here after p iteration, in fact you didn't came back before n iteration, which is the size of the cylinder. Okay, and so now that I begin by n, I can apply my mixing assumption. So in fact, this will be smaller. That so I have my double sum of. So what will appear is the measure of A prime, the measure of A, and the mixing part, which is constant, and alpha of J minus G, no, G minus N, okay, and the measure of the cylinder. Okay, and so now it's finished. Why? Because this one decay exponentially, so this is my 3b. This one also, so in fact, okay, so what is this? So you can approximate this one, and we have 1 plus, so C. This, the smallest one is alpha 0. So how much there is G minus N, so I can put G here. So this one is exponentially, so there is this C0 exponential minus H0N, and there is the sum of say A prime. So in fact, so this goes to 0, so you take G such that this goes to 0, and this is, in fact, you can prove that this goes to my extremal index times T. So in fact, this is how, this is a sketch of how we prove that for the periodic point, this Gn goes to 0. So just to finish, so in fact what you can see is that for general system, you can have exponential law if you assume decay of correlation. So if you just look at the measure on the skew product, the invariant measure for the random dynamical system, it's easier to obtain exponential distribution. And if you want an exponential distribution, until now, there is just result for random subshift of finite type. So depending on which mixing assumption you put, you will have exponential law, or for almost every point, or a result for every point, but for periodic points, you will have the extremal index. Thank you very much.